So, chapter 6 is about energy and thermodynamics. And the most important thing to remember about energy is that it can't ever be created or destroyed. It can only change forms from one to another, or it can move around and flow from one setting to another. But that's the first law of thermodynamics, the law of conservation of energy, that you can't ever destroy it or create it. So most of the time what we talk about is kinetic energy and potential energy. And kinetic energy is when things are moving, but potential energy is when it has the potential to move, right? So imagine if you had a ball at the top of that slide and you just sort of put it up there. That's got a lot of potential energy because it could move. But if you start rolling the ball down the slide, then it changes into kinetic energy. So it actually moves, and that's, kinetic. So, we talk about chemical reactions, and there's a lot of energy going back and forth in chemical reactions, but it's important to realize that it doesn't ever get destroyed. So we measure energy in joules usually, but there are calories that we use also, and this is not an SI unit, but we do use it a lot. And so 1 calorie is defined as 4.184 joules. That actually has a lot to do with water because that's the specific heat of water. So if a calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. It's important to realize these aren't the calories that you eat. They're sort of, but the calories that you eat are actually a kilocalorie. So it's 1,000 of these. So it's this is just a little tiny calorie, like a mini one. So this is important to realize, and that 4.184 joules will come into play again later. You'll see that number pop up over and over because that's actually the specific heat of water, because that's the definition of a calorie. So when we talk about thermodynamics, we are really studying the amount of heat that flows back and forth from the system and the surroundings in chemical reactions. So you've seen endothermic and exothermic processes when you use these hot packs and cold packs that you see in the stores all the time. When it gets hot, really, really hot, that's like the hot pack, that would be an exothermic chemical reaction happening inside of that pack. And if it gets cold, that's an endothermic reaction happening inside of that pack. So an endothermic process absorbs heat, and that's why it gets cold when you feel that pack. But if you think about it, anything that has heat on the left side of the arrow in a chemical equation or energy is going to use the heat up to produce the products. So baking a cake, we say cake batter plus the heat yields the baked cake. So even though you might not really think about it as absorbing heat, it is on, it's like an ingredient you need to get to that baked cake. So the same thing with melting ice. You take ice, solid water, plus heat, and it becomes water liquid. And an exothermic process would be one that produces heat. So if you take wood and burn it in oxygen, you're going to get, carbon dioxide and water vapor and a whole lot of heat. But you wouldn't really think about it if you freeze water. You start with liquid water, and then you get solid water plus heat out of it. You don't really think about that when you freeze water, but the heat that's coming out of the liquid has to go somewhere. You can't get the solid ice and then just the heat doesn't go anywhere. It's produced as a product of the reaction. So when we look at a system, the system is going to be whatever is happening in the actual reaction, and the surroundings are everything all around of it. So the surroundings are the outside of the flask here, and right inside the flask, and right above the flask. Everything is around it. And heat, we call it Q. Heat is energy that's transferred between a system and its surroundings. And it's important to realize that heat always flows from warmer objects to cooler objects, always, every single time. From warmer to cooler, never the other way around. So that's how those heat packs work. Sometimes, it gets hot or cold because the heat is flowing in or out of the surroundings. So before a reaction occurs, everything's at the same temperature, but if the reaction causes the temperature of the system to fall, then heat flows from the surroundings into the system. So heat goes from outside inside, and it feels cold. So if the reaction causes the temperature of the system to rise, heat flows from the system and into the surroundings. So it goes out, and that's why it feels hot. So the heat of reaction Q is going to be just a measure of the amount of heat that is exchanged during the reaction. And we're going to calculate Q. All right, so for right now, if Q is negative, then we can see that it's an exothermic reaction. The heat is coming out of the system and going into the surroundings. And we can feel that heat coming off. That's an exothermic reaction. But if Q is positive, the heat is going from the surroundings into the system. You're adding heat, and that is an endothermic reaction. So in an endothermic reaction, everything gets colder. Heat gets absorbed. Energy is added to the system because it comes from the surroundings into the system, and Q is positive. But in an exothermic reaction, everything gets warm, and energy is released from the system, so Q is negative. Okay, a calorimeter is something that we use to measure, what's happening during chemical reaction temperature-wise. So this is a bomb calorimeter that we're seeing right now. You can see it says, cutaway of the steel bomb, cutaway of the insulated jacket. There's graphite in there. There's some sort of ignition coil. There's a motor that stirs it around so that, everything is the same temperature. And there's a thermometer. So we will use calorimeters in our calculations, and we'll actually do a lab next week with calorimetry. We're going to use a much simpler calorimeter, which includes 2 styrofoam cups stuck inside of each other that's covered with a thermometer stuck in the lid. And that is our calorimeter. It's much more simple, but it still gets the job done. We still have kind of an insulated system, even though it's not perfect, and we still do have a thermometer, and we can stick it directly into the system and figure out what's going on temperature-wise with that change. So each substance that you put in a calorimeter requires a different amount of heat to raise its temperature, and you have to define a heat capacity when you use a calorimeter. Okay, so a heat capacity is the heat required to raise the temperature of the whole substance 1 degree Celsius. Okay, so whatever you put in there, that would be the heat capacity of the calorimeter. So every time you use a calorimeter, the heat capacity is different. So when we do a problem, you'll be given the heat capacity of a calorimeter. However, each substance in a calorimeter, there's a specific heat, and that is the amount of the heat required to raise the temperature of 1 gram of that substance 1 degree C. The last slide said the whole substance, see, the whole substance 1 degree C. It doesn't matter if you have half a gram in there or 10 grams in there. The heat capacity is of the calorimeter. But the specific heat is a substance. It's something you can look up in a book. Okay, you can look these up in tables. I think we have an appendix that has a whole bunch of specific heats in our book, and you can look up this value. So it's a little bit more specific than, 1 calorimeter experiment. But the way we got all these, the way chemists calculated them all is from calorimetry experiments. So that is really helpful to have. So we have 2 equations that we use to do calorimetry problems. One of them uses the heat capacity of a calorimeter, and that is Q equals negative C delta T. Negative C, well, C is the heat capacity of that calorimeter. So if you get a problem that says the heat capacity of the calorimeter is, that is when you use this first equation. Using specific heat, Q equals S times M times delta T. Okay, S is the specific heat, M is the mass, and delta T is the change in temperature, just like this delta T. Okay, so let's look at a sample problem. Calculate the heat absorbed by 15 grams of water to raise its temperature from 20 to 50 degrees C. Okay, so water has a specific heat of 4.18 joules per gram degree Celsius. Remember we said that we'd see that 4.18 pop up again. Water is, very specific with the 4.18 joules per gram degree Celsius. So we're going to use Q equals S times M times delta T because we don't have a calorimeter in this problem. So we're going to say S is our 4.18 and M is our mass, that's 15 grams. And our delta T is the change in temperature. Okay, so we just go 50 minus 20 is 30. And we multiply those three things together, 4.18 times 15 times the 30. And we get 1.88 times 10 to the third joules. Okay, so that's the heat absorbed by 15 grams of water. All right, it's not a hard problem. It's just pretty much plugging in the numbers. But let's look at this next problem. We have a 0.562 gram sample of graphite burned in a calorimeter. Now we have a calorimeter here. The temperature rises from 25 to 25.89 degrees C. So now we're given a heat capacity of the calorimeter at 20.7 kilojoules per degree Celsius. How much heat is generated by the reaction? Okay, so this time we're going to use our Q equals negative C delta T, and we're going to put our negative C in here. C is 20.7 kilojoules per degree C. And our delta T is 25.89 minus 25. That's just the change in temperature. And we don't really need to do anything with this 0.562 gram sample right now, because they're just asking us how much heat was generated by the reaction. So by the whole reaction, we just multiply that out and we get negative 18.4 kilojoules. But we'll see this problem again in a little while when we start to do more specific things with this calorimeter. All right, so enthalpy is something that is related to the heat of reaction. We measure it at constant pressure and we call it a state function. A state function doesn't matter how you get there, it only matters where you start and where you end up. It's a little bit like altitude. Change in altitude, it doesn't matter if you take path A and you go up these 12 miles all the way up this hill, or if you take path B and you go 5 miles straight up the side. Your change in altitude doesn't matter. It starts at 0 and you end at 10,000 feet. It doesn't really matter how you get there. That's how far you went, how high you went. Now your work put out might be a bit different, but your altitude is a state function, and it doesn't matter, if you went up and down 12 times, your change in altitude is still just the 10,000 feet. Okay, so enthalpy is kind of the same way. We measure change in enthalpy as a change. So, it says DH here. That means delta H just because sometimes the equations get a little bit messy, but you can understand what I mean when we say we measure delta H. So this is just a graph of the energy of the reactants, and then it goes up over this activation energy. Here's the energy of the products, but the change in energy is only the difference here between the reactants and the products because we're measuring enthalpy. So again, over here on the right side, we have the reactants starting up here. We go up above this activation energy and we end up down where the products are a lower energy. And again, we have a change. Delta H is just the difference between the reactants and the products. It doesn't matter that it went up in between. So we can just subtract this, okay? And we get the H of the products minus the H of the reactants, and that's QP. Okay, so it's still the heat, but it's the heat in a specific way. It's the enthalpy. Okay, so we're going to call delta H the enthalpy of reaction. And the way they get the values for these delta H's are from a lot of calorimetry experiments, doing them over and over again. So I'm really glad that there are some chemists out there who spent the time to do that for us. Okay, so a thermochemical equation is when you have everything written out and it includes delta H. So that is propane burning in oxygen. Okay, and your delta H, your enthalpy, is negative 2,044 kilojoules. Okay, so that means that it's the same enthalpy of reaction for 1 mole of propane, because we have 1 mole here, and it's for 5 moles of O2 because there's 5 moles there. The same as it's for 3 moles of carbon dioxide, for 4 moles of water. It's for the whole reaction as written. Okay, so remember this problem from a couple minutes ago. The 0.562 gram sample of graphite burned in the calorimeter, and the temperature rises. So now the question before was, if the heat capacity of the calorimeter is this, how much heat was generated by the reaction? Now we're going to ask a slightly different question. We figured that out to be negative 18.4 kilojoules. That's how much heat was generated by that whole reaction for the 0.562 grams. But now we're going to ask, what's the enthalpy of reaction? Okay, so what does that mean, the enthalpy of reaction? It means that for this chemical reaction right here that's written, what is this enthalpy of reaction, this delta H? Okay, so we're going to start the same way. We're still going to figure out how much heat was generated by the reaction. And that's a negative 18.4 kilojoules. But that's for this 0.562 gram sample. That's not for like 1 mole of carbon or anything like that. We have 0.562 grams of carbon. So we're going to do this using dimensional analysis. We're going to start with our 1 mole of carbon because that's what's given in our chemical reaction. Convert that into grams because we have grams. And now we're going to take our 0.562 grams and our 18.4 kilojoules. And we know that there are negative 18.4 kilojoules for every 0.562 grams of carbon that we burned, because that was the heat exchanged during that whole reaction. And that was for 0.562 grams. So we just stick that in as a conversion factor, and we get negative 392 kilojoules is our delta H. So I hope that makes a little bit of sense. It's really just a matter of realizing that, let me go back a little bit. It's a matter of realizing that this question, how much heat is generated by the reaction, is just for this 0.562 gram sample, and that to calculate the enthalpy of reaction, you need to calculate it for 1 mole. And so you need to convert the moles into the grams and then use what you've calculated for the heat to get the enthalpy of reaction.